What's up, guys? My name is James Jones. This is my Lab 5 where we choose our own adventure. So, for this lab, I wanted to analyze the motion of a basketball shot as it went from my hand to the hoop and compare this to a computational model that I'll create based on this data. And my goal in this lab was to predict the max height of the ball in an ideal scenario and to analyze the changes of energy within that system. So, the first thing I had to do was analyze the motion of my shot in Tracker. As you can see here, I simply went frame by frame as the ball left my hand until it got to the hoop. And as you can see, Tracker automatically made these two graphs and plotted the data for me on the side. So before I got to making my computational model, I first had to find the initial velocities that I could use for our system conditions. And to do this, I found the initial x velocity by just comparing the velocity in the second frame to the first frame and dividing that by the change in time. This is actually the fifth frame. But I divided it by the change in time between those 5 frames and got 3.43 meters a second in the x direction. And for the y velocity, I used this kinematics formula down here to get the initial velocity that would get me to the max height that we found in the experimental data. So basically what I did was plug in the components here. For the final velocity was 0. We're solving for the initial velocity, so I didn't have anything for that. The acceleration was due to gravity, was negative 9.8, and the change in height was 1.653 from the initial position to the max height. And we basically just solved this equation for the initial velocity, and we got that our initial velocity in the y direction was 5.69 meters per second. And another thing that we need for our model was the momentum principle and the energy principle to properly model the scenario. The first thing that we used was Newton's second law, as we use this equation to determine the velocity based on the max height, which we just went over. And then we used the momentum principle to update the velocity in our code, using that the final velocity equals the initial velocity plus the net force divided by the mass times the change in time. And we used this in our code loop to find the new velocity at each point. And then we also use the energy principle to determine the energy going in and out of a system, with the total change in energy equals the change in kinetic energy plus the change in gravitational potential energy, which would equal 0. The kinetic energy equals 1/2 mass times velocity squared, and the potential energy equals the mass times the acceleration due to gravity times the change in height. So moving on to our computational model, first we had to put in our initial conditions, which the mass of our basketball was 0.62 kilograms. Our initial position according to Tracker was this vector right here. Our initial velocity we got based on how we said in the last 2 slides. We got our initial x velocity be 3.43 meters per second. Our initial y velocity be 5.69 meters per second. Our time starts at 0, and we're going over at a rate of 0.01 seconds per iteration. And we also put in the acceleration due to gravity. Then if you look down here, this is where we apply the momentum principle to update the velocity of the ball in each iteration. As you can see here, it's the same formula as we just went over in the last slide. And we also use a derivative of this formula to update the ball's position at each point. And we calculate the net force using the ball's mass times acceleration due to gravity in the y direction. And then over here is where we're calculating our system's energy. So we had this loop go until 1.033 seconds, and that's how long it took for our shot to reach the basket. And then here we just have our initial kinetic energy, our initial potential energy. And then down here, we're finding the change in kinetic energy and the change in potential energy and the change in total energy in each iteration, just like we did in our previous labs. So moving on to the results, you can see that this is the graph that our glow script outputted, which looks very similar to what actually happened in real life. If we compare our experimental to our model data, you can see that the lines match up very well. They deviate a little bit at the end here, but we can say that's mostly due to human error and our lack of accounting for air resistance and other environmental factors. If we look down here in our change in energy, you can see that the total energy is conserved as we move through the system. It's just that the potential energy from gravity changes into kinetic energy as we get towards the end of the system. And then here is simply our y position versus time graph that we got from GlowScript that shows the same movement as we would expect to see from the graph. So in our discussion, we got what was our experimental max height versus our predicted max height. Our experimental max height was 2.129 meters, and our predicted max height was 2.09942 meters. And as you can see, these results are very close, so it shows that our predicted model is performing exactly how we expected it to, with just slight differences due to human error and air resistance and things like that. And was energy conserved in our system? As you can see in the previous slide, the answer to that is yes. The total energy in the system was conserved as the potential energy due to gravity is converted into kinetic energy at a constant rate. And that will be it for my Lab 5. Thank you for your time and have a good day.